Hey everybody, this is that lecture video I promised you about sample size calculation. It says down here hss2383. That's because this was originally from my fourth year class. Don't worry about that. This is actually I'm recording for my second year class, hss2381, statistics or quantitative methods, whatever you want to call it. We make up these fancy words like quantitative methods, when we really mean statistics, and we do that because we know people are afraid of stats and we're trying to be nice. That's why. So let us begin, children. Right? So I want to acknowledge that these slides are originally stolen from my good friend Nick Berriman, who is a statistician over at the Children's Hospital of Eastern Ontario. I originally had him give this guest lecture in my class many years ago, and I stole his slides. There, I admit it. I stole his slides, and now he knows. Now the world knows I'm a thief, but I'm giving him credit for these beautiful, beautiful slides. The example we are going to work through today is a simple one. It's this. You got some doctors, some clever doctors who have invented a pill that we think is going to reduce blood pressure. Okay? It's going to reduce blood pressure by some amount, and we want to find out if it works. How are we going to find out? We're going to have a study. That's what research is all about, doing studies to see if our stuff works. Okay, but if we're going to do the study, how many people do we need in our study? And this is a classic statistics question, a sample size computation. There are lots of ways to compute sample size, and it depends on a lot of things. But we're going to take a very simple approach today, and at the end of which I'm going to give you a couple of formulas that will work only in very specific circumstances. Because it's a second year class and you're not statisticians, so I'll keep this as simple as possible. The thing is, if we have too few people in our study, we're not going to be able to detect a change in blood pressure even if there is one. Because there's variations, right? There's noise in the system, and we need sufficient people such that there's sufficient sensitivity in our study to get an actual effect separate from the noise. On the other hand, if we have too many people in our study, it's going to cost us a lot of money, and some people are going to be exposed to risk for no particular reason. As well, we run the risk of detecting a lot of spurious stuff that isn't real. Right? But the real motivation we have for keeping our numbers down is that it costs a lot of money, especially drug trials. So we want enough people, but not too many people. Okay, so we have, again, a study that looks at whether or not this new pill changes blood pressure. So what will the study look like? Well, ideally, we're going to have a person, or maybe persons, and we check their blood pressure. Then we give them the magic pill. Okay, hey, take this pill, fantastic. And after they take the pill, they check to see if their blood pressure has changed. Okay, that would be the simplest way of doing this kind of study. It's a retest. The same people are tested twice, once before the pill and once after the pill. One group test. Great. There's another way, of course. We could have two groups. We can have people check their blood pressure. One group takes the pill, the other group doesn't take the pill. Right? They take the placebo instead. Sorry, those things should have come down in different order than they did. And then we see what the difference is in the two groups. Right? So this would be the two-group method, and this would be the one-group method. The retest and two. But you see how this works, right? There are all kinds of different ways. But what we're looking at here is to see if the pill changes blood pressure. Okay. Now, an interesting thing happens. If I give you anything, your blood pressure is going to change. If I give you a sugar pill, if I give you a slap on the face, if I give you a shot of water, if I give you, a hamburger, your blood pressure is going to change. That's the nature of blood pressure. That's the nature of the world, is that there's variation. There's always going to be something happening. So one of the questions we ask ourselves is, how much of a change does it matter that convinces us that something actually happened? That's called an effect size. Put that in the back of your brain. We're going to come back to that later on. Okay? But first, we're going to focus on the one-group test. So we've got a bunch of people, or one person. We check the blood pressure at baseline, you take the pill, and we see how much it changed. Remember what the null hypothesis is. The null hypothesis says nothing's going on. It's the baseline state in science and in statistics. We begin with the null hypothesis. In this case, it's going to be, on average, the intervention is associated with no reduction in blood pressure. In other words, the pill doesn't work. We begin by assuming the pill doesn't work. So if I give a bunch of people a placebo or a sugar pill, or if I give them the actual pill that I'm testing, I should see comparable changes in blood pressure. I might see zero change. But like I said, blood pressure is going to change regardless because there's a lot of variability in the system. So one of the reasons for a control group is to say, well, it changes more so than the other group. Cool. Remember, we write the null hypothesis as H sub naught. So H sub naught, the null hypothesis, is the burden of proof. It's the baseline state. It's like in a trial situation. We begin by assuming the dude is not guilty, and we seek evidence to prove that he is guilty. The presumption of innocence, that famous thing. So much like in the criminal justice system where we have the presumption of innocence, and we seek evidence to be able to throw out the presumption of innocence, in science, we begin by presuming the null hypothesis to be true, and we seek evidence, i.e. the study, to throw out that assumption and replace it with a new assumption that the null hypothesis is not true and the alternative hypothesis is true. The drug does work. Right? So our study is designed to put the null hypothesis to the test. So we have a few scenarios here. So like we've covered earlier in this course, on the rows here, we have the possible outcomes of our study, or the possible outcomes of a criminal trial, same kind of thing. You can either find that the drug doesn't work, this top row, or we find that the drug does work, the bottom row. Right? In other words, the bottom row could be we find the man is guilty, and the top row we find the man is not guilty. Right? So the top row is the baseline state, no effect, the null is true, and the bottom run is we reject the null and we say, the alternative is true. Now, regardless of which one we find, there's going to be actual truth, because the study or the trial doesn't tell us actual truth, it just tells us the results of our appraisal of the evidence. Actual truth is whatever the gods say, okay? So this first column here tells us that in actuality, the null is true. The drug doesn't work. The man is innocent. And the second one says the drug does work and the man is guilty. So we have some options here. There are two scenarios in which we have done everything right. Okay? We can either say that the drug doesn't work and that's true, or we say the drug does work and that's also true. Yay, that's great. The two scenarios in which things go wrong are these two. The scenario in which we say the drug works but it doesn't really, or we say the drug doesn't work and it does really. So the first one is type 1 error. That's when we say the drug works, but in reality it doesn't. In other words, we said the man is guilty, but in reality he's not. So as a society and as scientists, we have decided that this is not acceptable. We want to minimize this chance as much as possible. We like to minimize this too. We don't want a lot of guilty men going free. We don't want a lot of good drugs not making to market, but we're willing to accept this more than we are the alternative. So that's the trade-off, type 1 and type 2 error. Fantastic. So this is the population distribution of the change in blood pressure. And it's the distribution if we assume that the null hypothesis is true. Right? Let me say that again. Because we begin from a conservative standpoint. We begin by assuming the drug doesn't work. If the drug doesn't work, let's say I take one person out of the population, one person, and I give him a sugar pill, placebo, which will be the same as the drug if the drug doesn't work. right? And we say how much his blood pressure changes. Because I said everyone's blood pressure changes a little bit. So let's say it changes by 5 millimeters of mercury. Okay, I write down 5. I pick somebody else. Same thing. I take the blood pressure and I give them a sugar pill or the drug. It doesn't matter. It doesn't work, right? And I see how much it changes. Changes by 4. Great, I write that down. I take somebody else. Same thing, changes by 10. Great. Somebody else, same thing, changes by 5. I've got 2 guys who change by 5 now. Somebody else changes by 5 again. 3 guys change by 5. I take somebody else. Theirs changes by 20. Oh my God, that's extreme. So as I keep doing this, a pattern will emerge. So most people, their blood pressure will change by, let's say it's 5. Okay, that's the hump of this curve here. This is my frequency distribution, where the y-axis tells me how many times I find that result, and the x-axis tells me the change in blood pressure that I observed. So if the drug doesn't work, if the null is true, I'm still going to get a typical response in terms of the change in blood pressure. It's going to be this amount in the center, whatever that is, 5. Remember that one guy who got 20? Well, he's unusual. He's out here in the extremes here. And somebody else, theirs changed by 0.1. They're extreme as well. They're down here. But most people are going to be in the center. So the mean is going to be a mean change that most people experience, even if the drug doesn't work, if the null is true. Okay, and this is a bell curve, as we talked about before in the class. And this is the magic of statistics: is that everything in the example I just gave you, any characteristic, IQ, height, whatever it might be, if I do that scenario, if I take one person, I measure it and throw them back in, and take another person, I measure it, throw them back in, I'm going to get this kind of distribution. Okay, so the width is a standard deviation, and the mean is that thing in the middle. And variance, of course, is the square of the standard deviation. So this is, again, what happens if I've got one person. One person, that's all it is. I take one person, I measure the change in blood pressure. If I've given them something, a glass of water, a sugar pill, whatever it is, a slap on the face, this is the distribution I get. For 2 people, that's the distribution I get. You start to see where I'm going with this, right? With 2 people, it gets a little tighter, right? So 2 people, that means I've taken 2 people out of the population, I've given them both a sugar pill, and I've seen how much their blood pressure changes, right? And I've written that down. And I've taken another 2 people, and I've seen how much their blood pressure changes, and I write that down. And another one, and so on, until I got 1 billion people. And most people, most pairs of people, will see their blood pressure change by this amount. Fewer people by these amounts. If I take 5, it gets even tighter still. 5 people at a time. If I take 10 people, you see the point. You see where I'm going with this, right? The more people, the tighter the distribution. In other words, sample size affects the width of my distribution. Increasing the sample size reduces the variability of the mean of the sampling distribution, right? So my standard deviation has, in fact, shrunk. We call that a standard error. And if you remember from earlier in the year, the standard error is the standard deviation divided by the square root of the number of people that I'm selecting. So as this n goes up, the error goes down. It gets smaller according to that formulation. Okay, so increasing the sample size is like reducing the variance. Now we could also reduce the variance by having a better measurement, because right now I'm using my sphygmomanometer, that thing that squeezes your arm to see your blood pressure. And sphygmomanometers, I get a cheap one that gives me like a wonky measurement. I can get a supreme digital one instead of the one I got from AliExpress for $5 from China. I can spend a couple $100 and get one that's made by German engineers, right? And that can reduce my variance without having to increase my sample size. But that can be expensive, so that's a bit of a trade-off, right? There's a trade-off between the cost of having more people versus the cost of a better device, for example. Okay, so like I said, when we did this, we assumed the drug didn't work. We can assume that because everyone's blood pressure is going to change. This is true for pretty much everything in medicine. Something's going to happen. There's variability in the system. Okay, but this is the distribution that we get. Now let's say in our study we get a mean blood pressure change of this amount. Let's say the distribution that we observe in the population of just stuff randomly changing, like, take a sugar pill and it changes by this amount, etc., is this, but we observe a change of like, 15, where the mean that we expect is like 5. Is that enough to say something great is happening? Or is this still expected? The question you ask yourself is, what does it take to convince you that maybe the drug does work? Because you know that the blood pressure is going to change anyway, according to a variety of stimuli. What does it take to convince you that this is the drug that is making a change and not this other stuff? Okay. Hopefully, what it would take is a really big change. The question is, how big of a change? So right now, our change that we observe is over here. If it was over here, you'd say, oh my God, that's so unusual. It has to be real. It's so much bigger than expected. If it was down here, same thing. It's so low that maybe it's suppressing blood pressure change. So something's going on. So we need a cutoff to determine whether or not something's actually going on. If you remember earlier in the year, we said that cutoff is this. If it's greater than this arbitrary cutoff, then you're in our rejection region, and we say that, something's happening here. It's so unusual, so extraordinary, that maybe this null hypothesis situation isn't real. Maybe I got to reject that null. And if I reject that null, what I'm left with is the alternative, which is something's going on. And I can reject the null either at this end or at the other end. Right? I can say my sample is extraordinarily large compared to what I expected, or my sample is extraordinarily small compared to what I expected. In either case, it's extraordinary. So much so that I got to reject the null that gave me this curve and say, it's so unusual, it's something special. Reject that null. Reject that null. Okay. So to summarize, if this is the distribution of mean blood pressure change that we would expect in a population if the null hypothesis were true, then if I get a sample over here in this red area, it is so unusual, I can reject that null hypothesis and say, this is nonsense. The amazing thing is, that range there, that's the type 1 error. That's the risk I take of rejecting the null incorrectly. Because remember, I'm saying that if it's over here, I got to reject the null because it's so unusual. But what if I'm still wrong? What if, in fact, the null is still true? That's the risk of rejecting the null incorrectly. That's the type 1 error. Okay? By the way, my sample, let's go over here. Let me show it over here. Right? This is the null. The null is true. If my sample is over here, if in my 10 guys in my sample I see a mean blood pressure change of like 15 or something, what is this? What's that number? What does that tell me? Here, that's my change. What does it mean on the curve? Well, that tells me that's the probability of having observed that mean change if the null were true, right? Because this is just probability. Our frequency distribution is a probability. I'll say it again. This, on my x-axis, that's the actual blood pressure change that I observed in my sample. But where it intersects with that curve, where'd my cursor go? Hey, cursor. There you are. Okay? That's the probability of getting that mean change if the null is true. Okay? What do we call that? That, my friends, is the p-value. Dun, dun, dun. Right? The p-value is the probability of getting what you got if the null were true. So, back to this slide now. We said this red area, that's type 1 error. Fan-freaking-tastic. Okay. So, if the null is true, then the rejection region is the type 1 error, or the risk of incorrectly rejecting that null. So we usually say that cutoff, that's alpha. That's the probability of incorrectly rejecting the null. Alpha, Greek letter alpha. So, now that was all about if we assume the null were true. What if we assume the alternative is true? What if we assume, you know what, the drug does work? It changes blood pressure, right? How much? Well, on average, it's going to change it by a certain amount. But even if it changes blood pressure by a certain amount, not everyone's going to change it by the same amount. Most people will change it by and fewer people will change it by a little less, and fewer still by a little less, etc. So we're still going to get this bell curve of distributions of change. It's going to just be moved over based on how much we think the blood pressure is going to change. Okay? Now, before I show what that looks like, I have to tell you that type 2 error we usually call beta. Type 1 error is alpha, type 2 error is beta. And type 2 error, again, is the risk, the probability of falsely accepting the null or falsely failing to reject the null. So we're going to say now, let's say that our pill changes blood pressure by 10 millimeters of mercury. That, by the way, is the unit of blood pressure change, millimeters of mercury. Okay, so it says it does that. Fantastic. So this is the distribution. The yellow part is the alternative distribution. Let's go over what that means. This means that, on average, most people will see a blood pressure change of 10. Fewer people will see a blood pressure change of 9. Fewer still of 8, etc., etc., etc. A very small amount will see a blood pressure change of 84. A very small number will see a blood pressure change of like 0.1, whatever it might be. But most people will see it around here. Remember, if it didn't work, the blood pressure change would be like 0 or something like this, whatever it might be. Okay. So the difference here between the mean of the null distribution and the mean of the alternative distribution, that's how much change we expect. That's the effect size. In this case, we said the effect size is 10 millimeters of mercury. Okay. What's all this blue stuff? Well, this blue stuff here, that's the risk of incorrectly accepting the null, incorrectly failing to reject the null. Remember, we never actually accept the null. I'm a stickler on that. We always fail to reject it. Right? I will say a couple times in this lecture accepting the null because sometimes I have a hard time figuring out a different way to phrase it. But in an exam scenario, in real life, we never accept the null, we just fail to reject it. So again, this red part is a probability of incorrectly rejecting the null, and the blue part is the probability of incorrectly failing to reject the null. Look what happens now. As I shift my expectations, there's a trade-off. So I can say I want to really minimize my probability of failing to reject the null. But if I do so, I run the risk of increasing the other type of error. So there's a trade-off, right? And we make a decision about how much of one versus how much of the other. Now, let's talk about power. Power is another way of thinking about sample size. And we say power is actually 1 minus beta. Beta, again, is the type 2 error. 1 minus beta is the power. So we usually fix the alpha, the type 1 error, at 5%, 0.05. No reason, just tradition. Okay? Some people do it at 0.01, but most people say 0.05, 5%. So 5% is how much we will tolerate the risk of falsely rejecting the null, incorrectly rejecting the null. The beta then is the probability of incorrectly failing to reject the null, and power is going to be 1 minus the beta. Higher power means that things are more likely to be statistically significant. Okay? And the further apart those distributions, the higher the power. The further apart the distribution, though, that's the effect size. So let's look at this now. We've got the type 1 error fixed. It's not going to change. The rect par is not going to change now. We're saying that's 5%. But if I move my effect size, I get less type 2 error. What does that mean? Okay, the effect size, again, is a distance between these two peaks. That's how much effect I can detect, how much change in blood pressure I can detect. Here we said it's 10 millimeters of mercury. Here maybe it's 20. Here maybe it's 30. You see, the more I'm able to detect, the less error there is. If I want more fine detection, if I want the ability to detect something really, really tiny, I got to be able to accept more error. There's a trade-off there too. So how do I maximize power? Let's see how to maximize power. Well, I can change my sample size. Well, before I said if I moved my curves further apart, if I said I'm willing to compromise the fineness and the resolution of my detection, then I can reduce the error. Another way is to just increase the number of people in my sample. Here I've doubled the sample. See, here to there I've doubled the sample, and the blue part got smaller. So the amount of type 2 error got smaller. Here I've quintupled the sample size. It got smaller again. So in other words, the more sample, the less error. Yay! Okay. That's a long way of saying that sample size gives us more ability to detect more resolution with less error. So now it's time for me to show you some formulae for detecting, for calculating sample size. To do this, you're going to need a few things. You're going to need to know the variance, the expected variance of the thing that you're measuring. Remember, variance is sigma squared. It's the square of the standard deviation. We're going to fix alpha at 0.05, and we're only going to use two-tailed tests, and we're going to say that our power is 80%. Remember, power is 1 minus beta. Delta is our effect size. That's how far apart those curves are. And again, that's the size of the thing that we're going to detect. Okay, and this is approximately the formula that we're going to use. So again, in order to compute the number of people you need in a one-group study, this is just for a single group study, looking at, see if blood pressure changes in this group after they take the pill. Okay, so the delta is going to be how much of a change it can detect. Let's say it's 10 millimeters of mercury. The sigma squared is the variance expected, and here we have a multiplier, 8. So let's say I plug in my numbers and I get, 9.1. How many people are in my sample? 9.1? You can't have 9.1 people. No such thing as 0.1 people. So do I round down? Do I get 9 people? Well, if I round down, I don't have enough people because I said I need 9.1. 9 is less than 9.1. So I need the next integer up. If I get 9.1, I need 10 people. If I get 9.6, I need 10 people. If I get 9.9, I need 10 people. I round up to the next integer, always. Okay, example. You've got a standard deviation in the change in blood pressure you think is going to be 7. So the variance is going to be 49. By the way, how do I know it's going to be 7? I know this from a couple of ways. Either I go to the literature and see what people have been doing and theorizing, or I run a pilot study, or I look at animal studies. I need some kind of experimental input to give me that number, that expected variance. 49. So we're fixing the alpha at 0.05 and the power at 80%. It only works. The formula I'm giving you only works in this scenario. If the alpha is not that and the power is different, this formula will not work. And we're going to detect a delta, a change of 5 millimeters per mercury. Right? So if we plug it in that previous formula, I get 8 times 49 divided by 25. I'm going to get a number that rounds up to 16. Fantastic. I need 16 people. What if there are two groups? Do I double that? No, my friend, no. So if you need two groups, you're going to need a control group and an experimental group. Like earlier in this lecture, I showed you we have some people, some of them get the drug, some get a placebo, and we see what the difference in the change is. That's a two-group test. So the two-group test, the formula is going to be that. Same assumptions. Alpha is 0.5, power is 80%. Okay. Notice that instead of 8, we have 16, just double, but this is the n per group. You need n for the control group, n for the test group, n for the placebo, n for the drug group. So if I plug in all my numbers here, and I get n per group of 9.1, how many people do I need in my study? Well, we just said we have to round up, right? So 9.1 per group means 10 per group, which means 20 people total. What some people do, they take 9.1, multiply it by 2, they get 18.2, and they round that up to 19. They say, wait, we need 19 people. No, you need 20 people. You round up first, then you double it. See that? Cool. Okay. This is the sample size per group, like I said. Right on. Notice this is 4 times as large as the previous one, because it's not just 8, it's multiplied by 2 to get 16, and you multiply it by 2 again because we got 2 groups, so it's 4 times as large. Okay, the example. You want to compare patients randomized to placebo with patients who are getting the new drug. Okay, again, the standard deviation is 7, alpha is 0.05, power is 8%, and we're looking for a change in 5, and then we get 64. Remember, before we had 16, same scenario, okay, but now we have 64. You can go through that example and get those numbers yourself if you want. Remember, sample size is affected by different types of outcomes. We just looked at change in blood pressure, a continuous ratio level variable. But sometimes we look at things like yes/no outcomes. Right, so we need a different formula for that, or time to event. Don't worry what that means. It's like how long will people live in our sample. Different kinds of designs. So in this class, you learned about cohort and case controls. Now we just saw a randomized control trial. Don't worry about those things mean too much, but recognize that different designs require different sample size formulas. And of course, oftentimes we don't have enough money to recruit 1,000 people. I got enough money to recruit maybe 20 people. If that's the case, I'd have to compromise on my effect size, a bigger effect size rather than smaller, or other kinds of compromises. So in summary, you need more people if you've got big variance. You need fewer people if you're willing to detect a larger effect size. You need more people if you want to detect a smaller effect size. It's going to depend as well on your type 1 error and your type 2 error. Obviously it's late. It's like 2 in the morning and I'm losing steam. So I think I'm going to finish off here. Just remember, there are 2 formulas for sample size calculation I've given you. One is for 1 groups and the second one is for 2 groups. And just keep the type 1 error and the type 2 error separate in your mind. Remember how to calculate standard error and you'll be fine, my friends. That is all. See you later.